Section 1 Introduction. Let's dive into the fascinating world of large language models, LLMs, which have been making waves in the field of artificial intelligence. These models are known for their vast number of parameters and their impressive ability to generate text. They've shown great potential in a variety of applications. However, there are concerns about their accuracy, their ability to reason, and the safety of the content they generate. One potential solution to these concerns is the concept of self-correction, where LLMs improve their responses based on feedback from their previous outputs. But there's a mystery here. If an LLM can self-correct, why doesn't it just give the right answer the first time around? This paper aims to unravel this mystery by taking a deep dive into the self-correction abilities of LLMs, with a special focus on reasoning. To do this, we first need to define what we mean by intrinsic self-correction. This is when a model tries to fix its initial responses using only its built-in capabilities, without any external feedback. This is important because in many real-world applications, high-quality external feedback isn't available. Plus, it's crucial to understand what LLMs can do on their own. Despite the optimism around self-correction, our research shows that LLMs struggle to fix their previous responses in this setting. In fact, their performance often gets worse after self-correction. This is a surprising finding, as it contradicts previous research. Upon closer inspection, we found that the improvements in these studies were due to the use of oracles to guide the self-correction process. When these oracle labels aren't available, the improvements disappear. We also looked into the potential of multi-agent debate as a way to improve reasoning. This is where multiple instances of an LLM critique each other's responses. However, our results show that this method is no more effective than self-consistency when considering an equivalent number of responses. This highlights the limitations of this approach. On the other hand, while self-correction may not be great for enhancing reasoning, it does show promise in other areas, like changing the style or improving the appropriateness of responses. So, it's important to understand the subtleties and identify the underlying reasons. We see self-correction as a form of post-hoc prompting, where the prompting involves the responses of LLMs. We looked at situations where self-correction is truly beneficial, specifically when it provides instructions or feedback that standard prompting misses. Our analysis shows that the improvement attributed to self-correction in certain tasks may be due to a poorly crafted initial instruction that is overshadowed by a carefully crafted feedback prompt. In these cases, incorporating the feedback into the initial instruction or crafting a better initial prompt might yield better results and lower the inference cost. Given our findings, we encourage the community to approach the idea of self-correction with skepticism and caution. We also encourage further research into methods that can genuinely correct reasoning, such as incorporating external feedback. Now, let's take a step back and look at the broader context. The idea of self-correction has its roots in the foundational principles of machine learning and adaptive systems. Early work in neural networks involved adjusting model parameters iteratively in response to prediction errors, a process that can be seen as fixing errors using feedback from training data. The introduction of reinforcement learning added another layer to self-correction. In this paradigm, agents optimize their strategies through interactions with their environment, constantly changing their policies based on rewards or penalties they receive. A significant advancement for LLMs was the incorporation of reinforcement learning from human feedback, RLHF. This method incorporates human insights, addressing challenges in crafting precise reward functions and mitigating unintended behaviors. However, this feedback often lacks immediacy as it traditionally integrates during training phases rather than in real time. Furthermore, corrections might not necessarily be reflected in specific queries during inference. With the evolution of LLMs, the idea of inference time self-correction has gained prominence. The discussion now revolves around whether these advanced models can recognize the appropriateness or accuracy of their outputs and, if needed, provide refined answers. For example, in the context of mathematical reasoning, an LLM might initially solve a complex problem but make an error in one of the calculation steps. Ideally, the model should recognize the potential mistake, revisit the problem, correct the error, and consequently produce a more accurate solution. However, the definition of self-correction varies across the literature, leading to ambiguity. As the field evolves, various terms like self-refine, self-critique, self-improve, and others emerge, each with its own specific context. A key distinction lies in the source of feedback. Is it purely internal, originating solely from the LLM, or does it draw from external inputs? Internal feedback relies on the model's inherent knowledge and parameters to reassess its outputs. In contrast, external feedback incorporates inputs from humans, other models, or external tools and knowledge sources. Given that high-quality external feedback is often unavailable, and acknowledging its evident advantages, we focus our investigation on whether LLMs have the inherent capability to rectify their responses. We call this setting intrinsic self-correction. For simplicity, unless explicitly stated otherwise, all references to self-correction in the rest of this paper refer to intrinsic self-correction. Section Summary. The paper explores the concept of self-correction in large language models, LLMs, and its effectiveness in improving reasoning capabilities. The study reveals that LLMs struggle to amend their initial responses through self-correction, and the performance often deteriorates. While self-correction shows promise in tasks like altering style or improving appropriateness of responses, it is important to understand its limitations and consider incorporating external feedback for genuine reasoning correction. Section 3. Can large language models self-correct reasoning? We're exploring a fundamental question. Can large language models, LLMs, correct their own reasoning? This is crucial because reasoning is at the heart of human cognition. It's how we understand the world, make decisions, and solve problems. If LLMs are to be truly useful, especially in critical areas like decision-making, education, or healthcare, they need to have strong reasoning abilities. We're focusing our research on this key question. To do this, we're looking at existing studies, conducting thorough experiments, and providing detailed analyses. We're trying to use existing self-correction methods to see if they can improve the performance of LLMs on reasoning tasks. We're using labels to guide the self-correction process, as these methods do. We're using a variety of datasets that have shown significant improvements through self-correction in previous studies. These include the GSM-8K, which is a set of 1,319 diverse grade school math word problems, the Common Sense QA, a collection of multiple-choice questions that test common sense reasoning, and the Hotpot QA, an open-domain multi-hop question-answering dataset. We're using a three-step strategy for self-correction. First, we prompt the model to generate an initial response. Second, we prompt the model to review its previous response and provide feedback. Third, we prompt the model to answer the original question again, but this time with the feedback. Our main testing is done on GPT 3.5 Turbo. We're trying to replicate the experiments described in the original papers. We're also testing GPT-4, the latest and most powerful version of OpenAI's model, to see how well it can self-correct. We're limiting the models to a maximum of 2 rounds of self-correction. We're using the correct label to decide when to stop the self-correction loop. Our results show significant improvements in performance, which is consistent with previous findings. However, we need to be careful in interpreting these results. In a real-world setting, especially when using LLMs to solve math problems, we don't know the correct answer. So, the performance improvement needs to be considered more carefully. To illustrate this point, we've designed a baseline based on random guessing. In this baseline, we still use the correct label to decide when to stop, but the correction is not done by the LLMs. Instead, it's derived from randomly guessing from the remaining options. This random baseline achieves a 100% accuracy after 4 rounds. However, it's clear that this is not a viable correction method. The results achieved with the use of labels might still serve as an oracle, indicating the presence of a perfect verifier that can judge the correctness of an answer. This could be useful in tasks like code generation, where we can use an executor and unit tests to check if the generated code works correctly. However, for reasoning tasks, like solving math problems, this setting seems counterintuitive. If we already know the answer, why would we need to use LLMs to solve the problem? This setting might be useful in situations where we want to understand the reasoning process, where the answer might be known, but we want to understand the detailed reasoning or explore different solutions. Section Summary. Large language models, LLMs, need to possess robust reasoning capabilities to be reliable tools in critical applications. In this section, the authors investigate whether LLMs can self-correct their reasoning by employing existing self-correction methods and conducting experiments on diverse datasets. The results show significant performance improvements, but the use of correct labels as an oracle for self-correction raises questions about the practicality of this approach, especially in tasks where the ground truth is already known. Section 3.2 Intrinsic Self-Correction. We've been discussing the concept of large language models, LLMs, being able to self-correct their reasoning. However, the evidence so far doesn't support this idea. So, we decided to focus on the results of self-correction that happens naturally, without any external influence. To do this, we stopped using labels to decide when to stop and evaluated the performance after 2 rounds of self-correction. What we found was that the model's performance actually decreased on all benchmarks after self-correction. This might seem counterintuitive, so let's delve into why this might be happening. We used GPT 3.5 to analyze the changes in answers after 2 rounds of self-correction. For one of the benchmarks, GSM-8K, the model kept its initial answer 74.7% of the time. When it did change its answer, it was more likely to change a correct answer to an incorrect one than the other way around. For another benchmark, Common Sense QA, GPT 3.5 was more likely to change its answer. This is because the wrong answer options in Common Sense QA often seem relevant to the question, and the self-correction prompt might bias the model to choose another option, leading to a high ratio of correct to incorrect changes. We also looked at the results when we used ground truth labels to stop the model from changing a correct answer to an incorrect one. But figuring out how to prevent these wrong changes is actually the key to successful self-correction. Here's an intuitive explanation. If the model is well aligned and the initial prompt is well designed, the initial response should already be the best one given the conditions of the prompt and the specific decoding algorithm. Adding feedback can be seen as adding another prompt, which might skew the model towards generating a response that fits this combined input. In a natural self-correction setting, this extra prompt might not help answer the question and could even bias the model away from producing the best response to the initial prompt, leading to a decrease in performance. You might be wondering if the self-correction prompt we tested was not the best one. Could other prompts improve performance? It's entirely possible that we could find a prompt that improves model performance on specific benchmarks. However, this would not align with the natural self-correction setting we're discussing in this paper. Searching for such a prompt essentially uses feedback from humans or training examples. The same strategy could also be used to optimize the initial prompts, possibly achieving better performance without needing additional model calls for self-correction. We're not the first to observe that self-correction doesn't necessarily improve the reasoning of LLMs. Other studies have shown that self-correction has potential across various tasks, but mathematical reasoning shows little improvement. Studies that incorporate external feedback or tools find that self-correction without such feedback is a relatively weak baseline. In our review of the literature, we found another potential approach for LLMs to self-correct their answers, allowing the models to critique and debate through multiple model calls. We tested this method on one of the benchmarks, GSM-8K, using the same prompt and replicating the experiment with the GPT 3.5 model, incorporating 3 agents and 2 rounds of debate. We also tested self-consistency, which prompts models to generate multiple responses and uses majority voting to select the final answer. The results showed that both multi-agent debate and self-consistency significantly improved performance over standard prompting. However, multi-agent debate only slightly outperformed self-consistency with the same number of agents. In fact, multi-agent debate significantly underperformed simple self-consistency using majority voting with an equivalent number of responses. Rather than labeling the multi-agent debate as a form of debate or critique, it's more accurate to see it as a way to achieve consistency across multiple model generations. The main difference is in the voting mechanism, whether voting is model-driven or purely based on counts. The improvement we observed is not due to self-correction, but rather to self-consistency. If we want to argue that LLMs can self-correct, it's better to exclude the effects of selection among multiple generations. Section Summary. In this section, the authors focus on the intrinsic self-correction setting and observe that after 2 rounds of self-correction, the model's performance drops on all benchmarks. They explain that introducing feedback through self-correction prompts may bias the model away from producing an optimal response to the initial prompt, resulting in a decrease in performance. Additionally, the authors compare the results of multi-agent debate and self-consistency methods and find that multi-agent debate achieves only slightly better performance than self-consistency, indicating that the observed improvement is attributed to self-consistency rather than self-correction. Section 4. Self-correction as post-hoc prompting. In the previous section, we noticed that language learning models, LLMs, often struggle to correct their own reasoning. However, there are instances where self-correction has led to remarkable outcomes, as shown in various studies. It's important to understand why this is the case and identify the underlying reasons. Self-correction can be seen as a form of after-the-fact guidance or post-hoc prompting. This differs from standard prompting, which we'll call pre-hoc prompting, in that it's applied after the LLMs have given their responses. We call the process of improving these prompts post-hoc prompt engineering. Self-correction can improve model responses when it offers valuable instruction or feedback that pre-hoc prompting can't provide. For example, if we're trying to make a response safer, it might be hard to guide a model to generate completely safe responses on its first try using only pre-hoc prompting. In these cases, self-correction can help improve the safety of responses through a detailed post-hoc review. However, this might not be the case for reasoning tasks. A feedback prompt like, "Review your previous answer and find problems with your answer," doesn't necessarily offer tangible benefits for reasoning. Even when we see a significant improvement in performance after self-correction, it's important to carefully consider the design of the prompt. For instance, if a response needs to meet certain criteria that can be easily specified in the initial instruction, like containing certain words, generating highly efficient code, or having a strongly negative sentiment, it might be more cost-effective to include these requirements directly in the pre-hoc prompt, rather than using them as feedback in the post-hoc prompt. We use the constrained generation task as an example, where the task involves generating coherent sentences using 20 to 30 input concepts. Instead of asking the model to identify missing concepts and then guiding it to incorporate these concepts through feedback, we can simply instruct the model to include all the concepts from the start. Based on this insight, we created a simple baseline by designing the prompt as, for example, concept, vest, serve, winter. Write a reasonable paragraph that includes all of the above concepts. We used concept coverage as the metric and tried to replicate the experiments using GPT 3.5 Turbo 0613. We also experimented with their self-correction approach to refine the outputs produced with our designed prompt. The results showed that our casually crafted prompt, standard prompting, (ARS), performed better than the post-self-correction results of the original study. Moreover, when we used their prompt to refine our outputs, performance actually decreased. Many outputs failed, like formatting issues, when applying the original study's prompt, requiring many regenerations, which is another potential drawback of self-correction. Our main goal here is not to argue whether a post-hoc prompt exists that can outperform the prompt we wrote casually. Instead, we want to encourage a more critical examination of self-correction experiments. It's not useful to use a well-crafted post-hoc prompt to guide the model in self-correcting a response generated through a poorly constructed pre-hoc prompt. For a fair comparison, equal effort should be invested in both pre-hoc and post-hoc prompting. Given the significant token costs associated with self-correction, researchers and developers should carefully consider its real benefits compared to what can be achieved with a pre-hoc prompt. Self-correction can still be beneficial for aligning responses with certain preferences. For example, it can be used effectively to make responses align with specific preferences, such as changing the style of responses or improving their safety. However, self-correction might not be effective when trying to correct responses for tasks in which LLMs find it hard to identify errors in their initial responses or assess the correctness of those responses. In this paper, we focus on the intrinsic self-correction setting. However, when we use external feedback for correction, the story changes. For instance, studies have shown that LLMs, when interacting with various external tools like search engines and calculators, can more effectively verify and correct their responses. One approach to achieve this is through external feedback. Another method is by leveraging self-consistency, as explored in a previous section. An example of this approach is tree of thought, where the reasoning of LLMs is improved through stepwise verification paired with self-consistency. As discussed earlier, the latency and cost of post-hoc prompting are higher than those of pre-hoc prompting. Therefore, if the feedback can be encoded in the initial instruction, pre-hoc prompting is the better choice. However, in cases where we want to use external feedback that must be given in conjunction with responses, post-hoc prompting becomes a more suitable option. Finally, we would like to offer some guidelines for comparison regarding self-correction. First, when comparing self-correction methods to other baselines, it's important to report the inference cost, like the number of calls or tokens. Second, avoid using a poorly designed pre-hoc prompt while crafting a carefully designed post-hoc prompt for improvement. Third, when the methods use external feedback, it's essential to consider whether the feedback is reasonable.